Thank you, Natasha. I just want you to imagine that you are on this red planet, okay? You have launched from Earth. You're just inside your small habitat. You're so thirsty, and then you reach to a water bottle. You take a sip, and then you drink it. But then, can you imagine, like, where do we get this water from on Mars? Because there's no lakes, there's no rivers. All that is just frozen ground with maybe a very thin atmosphere and dry too. So where do we get the water from? So that's what I have been working on mostly, to find and recycle water from the remote places in mostly outer space environments. My name is Abhilash. I am a space resource utilization engineer working at Hydromars. Just to give you a brief background, so how many of you think there might be liquid water on Mars? Do you think there's liquid water on Mars? So just to understand the concept of liquid water, we just need to understand how does liquid water form. So what exactly happens here? So if you look at this graph, I'm just not going to go into too much of detail. So here you see the temperature on X and pressure on Y. So at some point, we might have heard this term called triple point of water. So where water sort of exists in all three phases, that's solid, liquid, and vapor. So for water, it's 0 degrees Celsius in temperature-wise, and then pressure, if you look at it, it's 6 millibars. So first, let us consider Earth. So on Earth, we do have water in all three phases. So there's ice in form of glaciers, that's solid. There's lots and lots of water in the oceans, that's liquid. And there's a lot of water vapor as well. So the reason being, on Earth, the pressure is sort of 1 atmosphere, and then the temperature sort of varies. So since the pressure is high enough, we have water in all three phases. But if we look at Mars, the temperature is okay. The average temperature on Mars is minus 60 degrees Celsius, right? But at some point during the summers, the temperature goes slightly above 0. So slightly above 0, but then mostly it's negative. So that's why on Mars, mostly the water is in mostly two phases. That's in form of solid, that's ice, the frozen part, and then very little water vapor on Mars. But we just have to look at this pressure here. It's 6.1, the triple point. The pressure on Mars is also varies from 6.1 millibars to 10 millibars if you look at different latitudes, right? So since it hovers, the pressure sort of hovers around 6 millibars, there might be possibility for liquid water to form on Mars for a very, very short period of time given the temperature and pressure conditions, right? So if you look at this image here, this image is taken from Phoenix lander at morning 6 o'clock, and you can see sort of a little frozen patches on the ground, but then after a bit of sunrise of heat, it sort of evaporates back. So is it safe to say that there's sort of near surface water cycle on Mars? This particular study from Curiosity rover on Mars was published in 2015, which sort of hypothesized saying that the Mars surface, the Martian surface, which has these salts, like the soil is mixed with these salts called deliquescent salts. So what happens during the night time is at a given air column, so these salts sort of captures or absorbs the water and forms frozen brines during the night, right? And then it forms brine over the night, and then during the morning, when the sun is up, the heat just splashes on the ground, and then it sort of evaporates back, so forming a near surface water cycle. So this is sort of a theory, but can we really quantify how much of water can be trapped on the ground? So this was sort of my study during my doctoral phase. So this particular chamber you see here was built at Lilla University up in the north to recreate Martian pressure and temperature to see how much water can be quantified and can we really capture these waters. So just a quick description of the water that can be captured. So there are two experiments, important experiments that was done in that particular chamber. So you do remember the salts that I mentioned that is being found on Mars. So we selected 4 different salts and then exposed to these certain temperature and pressure along with a bit of relative humidity inside it. And we could capture certain water. I will quantify it. So in 2 different types. So here you see the complete just pure salts, but then this is mixed with the salt mixed with soil, not exact soil, it's a simulant. So we know the compositions of the Martian soil, we call it as regolith or simulant. So that is mixed with these soils to capture and see how much water can be trapped. So the first experiment shows 3.53 grams has been captured, and the second one is 2.2. So here you clearly see there are sort of chances where you can use the local resources to utilize or maximize the amount of resources that you need for longer duration missions. But once you have water, so that is one aspect of it. The other one important for us humans to survive anywhere is plants, right? Can we really grow plants on Mars? Let's compare Mars and Earth for a while. So what are the 3 important things for us to grow plants? Sunlight, water, and carbon dioxide. Do we have on all these 3? Yes, we do. But when we see Earth, we know Earth is really good and ideal for plant growth because we are growing plants on Earth. But how about Mars? Do we think it's really good? As I mentioned earlier, Martian soil do have these salts, and these salts are a bit toxic. And we cannot really grow plants directly, so there needs to be some sort of a modifications to be done. There needs more additional nutrients to grow plants. So there was an experiment that sort of we performed, which clearly shows that using the Martian simulant that I mentioned earlier to grow rice plants, can we really grow plants? So here are 5 quick images that I would like to bring it up. So you see the soil is sort of mixed with potting mix is nutrients, the additional nutrients that we provide to the plants. So it's mixed in different proportions. So if you look at the plants that has high nutrients, grows significantly well. But if you look at the 4th one, which is just pure soil or the Martian simulant, the plant growth is really, really bad. So what does this confine? So which means that water and nutrients are 2 important things for us to think of when we go for long duration missions. So we can talk all about Mars using resources and stuff like that, but that might be a few years down the lane. So before we travel to Mars, there are a few other steps. So initially, we start off with International Space Stations or low Earth orbit. We start off there, and then we test the technology on Moon, and then eventually move to Mars, right? But then why do we have to reuse water even in low Earth orbit? The one thing why we have to use these things is because the launch cost is significantly high. Just to launch 1 kilograms, it's roughly around $20,000 or $25,000. And also, once you have water, it's just not used for drinking. It can be used for hygiene, oxygen production, also to produce fuel. Other than that, we need to close water, and then rather than imagine a long duration mission, say you go to Moon or Mars, you cannot carry everything because you see the launch cost is significantly high. So you need to somehow close the loop and keep recycling it more and more. And this sort of provides more sustainability. So are there any technologies that is being doing right now? Yes, there is. There is a state of the art. And that state of the art is the International Space Station. So the water is being recycled in the International Space Station using this particular system called water recovery system. And it has 2 different modules. So it has water processing assembly called WPA, and there's urine processing assembly for UPA. I know it's not a nice thing to say when you're having your breakfast, but urine is sort of processed in a separate like module. So what happens, this is sort of the state of the art that is on the International Space Station, but it has its own drawbacks, right? So the technology is from 1900s, but then it was, 1990s, sorry. And then it was installed in early 2000s or late 2000s. And then you see how big, heavy, and complex it is. It weighs around 1,500 kilograms. And then, as I said, weight is equal to money. So it has to be reduced, and then it just processes water. So as I mentioned earlier, water is one aspect, and nutrient is other aspect. So water processor assembly on the ISS just provides water. So this is where we hydromars come in. So we try to provide solutions for water and nutrients. I would like to invite my colleague, the CEO and co-founder of Hydromars, Shorena, to speak about Hydromars.
Thank you very much. Amazing, amazing. I welcome everyone. As Abhilash rightly mentioned, our target is to recover water from anything you can find in space, whether it's urine, sweat, anything basically lunar or Martian regolith. And the company Hydromars was established in 2020 by myself and another co-founder that is also the founder of Hydromars' mother company called Scarab Development. And Scarab Development itself was established in 1970s after the United Nations conference with a target to propose different water solutions in different aspects of life. Today, Scarab is a cluster of 5 different companies working with the same technology concept, the core concept, but in a different business applications. And Hydromars is one of those companies where we basically use the core technology and we accommodate it to the conditions of space. We have 3 patents by agreement from our mother company. We have freedom to operate in US and also in EU countries, and we are currently considering doing it also for Russia and China. We have around 2,000 individual shareholders that support the company and our projects. There are several contracts with the European Space Agency and also Swedish National Space Agency we work with. We are currently the lead from the SNSA, or Swedish National Space Agency's project, where in collaboration with KTH, Lilla University of Technology, and SLU, we work on finalizing process and adapting it to one of the commercial space stations that will be orbiting and substituting the International Space Stations from 2026. And we will be testing our core technology in space already in 2 months from the Falcon 9 rocket from Vandenberg site, where we will be able to see what are the results of the core process in comparison to the process we receive here. Now, if we look at the market, as you probably know, the market has really experienced a lot of increase both in capital. Today it's around $500 billion industry, and there are several triggers that have contributed to this. One, and the most important, is the introduction of reusable rockets by private companies like SpaceX, whereas the cost per kilo has decreased from around 65,000 to 25,000. Another really important point is the introduction of electric propulsion, which means that we can today afford the more extended missions, like to lunar surface, for instance. Now, all of this has contributed to the big interest from private investors, venture companies, institutional investors, and also the emergence of new space companies that want to test their technologies in microgravity conditions. And the third, and our most favorite trigger that has contributed to the market, is the commissioning of the International Space Station by 2029, and as a result, introduction of new commercial space stations that will be a big platform for science already from 2026. Now, you see several companies here. We are currently in communication with 2 of them, which is Heaven, which is planning to test their first commercial space module already in 2026, and also a company called Axiom Space. That is the one that actually delivering astronauts to by their Dragon missions to the ISS, including, for instance, latest AX-3 mission with Marcus Wandt. Now, if we look at the technology, you can see here some of the products which Hydromars and Hydromars mother company has been involved. And for instance, before Hydromars was established, there were already some preconditions for technology being adapted to space. If you see the first image, you see the project with UNICEF called Sweat to Water, where the technology has been used to extract pure water from the sweat as a result of exercises from just regular people outside. And if you see images below, here you see our first generation prototype, which has right now, which is on the 7th floor, which we use for recovering water directly from human urine, which actually Abila showed you. Now, if you see here the conductivity of 0.89 microsiemens per centimeter, basically what this tells us is that the water is so pure that you have to add the minerals in order to make it drinkable. Now, this is also a potential market in space. Imagine you are in space for several months. You will experience a lot of health problems, let's say bone density. And if you have a type 1 quality water, you can add minerals just specifically for your health conditions. And that creates also a potential market maybe in 3-4 years from now. Just as an example, the water we drink from the tap is around 500 microsiemens. So 500 versus 0.89. Now, this is a project we were involved in for the past 2 years. This is the unit we developed, which was partially co-financed by European Space Agency, where Hydromars, together with the University of Southampton, was chosen and financed to test our core technology on the NIX orbital vehicle developed by European manufacturer called the Exploration Company. And now, what we do basically in this unit, we test our core process. We also have several parameters installed, like cameras, flow sensors, anything that can actually record the purification process while in space and bring us very important data for us to use it for our next iteration of products. It's important to mention that since the opportunity was very limited because we were restricted both for power, it's less than 20 watts time, which is 30 minutes of continuous microgravity in space, and also the space, it's 20 centimeters on 20 centimeters on 14 centimeters, basically a shoebox size. We had to develop everything by ourselves, and as a result, 60-65% of all components was developed by Hydromars in-house. Let's say this is the membrane module, one of the key aspects of water purification, which has been structured, designed, developed by us, and in the end it seems we overdid a bit because we received the factor safety of 10, meaning that even if Falcon 9's launch is 10 times more stringent, the module will be able to do its work still. Now, we finalized this project approximately in 14 months, and we delivered our project to the Exploration Company in their clean room facilities in Munich in December. So here you see the delivery of the payload, and this is how the payload is integrated to the NIX capsule. Now, the launch is expected to be in June, somewhere second half of June. It will experience the flight of approximately 3 hours, out of which 30 to 40 minutes will be continuous microgravity. And even if something happens during splashdown or the launch, it's completely automated, which means that we still will receive the data because there is communication with the ground from the space. A second project which we today perform on the 7th floor is basically what I mentioned earlier, a consortium project with KTH, LTU, and SLU, where we use urine provided by SLU and we test our processes. Now, since we're already sending the core process in space, what is left really is to finalize the product, because we need to have a pre-step and also post-step in order to finalize the recovery rate. So this is a target for this year, after which we will proceed with our plan of delivering a full-scale system for one of the missions to the ISS. Now, we received the offer from the Axiom, which is equivalent of approximately 10 million crowns, and which allows us of testing technology directly with a feed coming from astronauts' urine and astronauts working on the technology for a 20-25 days missions. This will be, and this is expected to be, the last validation mission before we approach commercial space stations and try to integrate the technology in their new modules. And if we look at the commercialization timeline, here you can see 2023 was very much into the R&D. 24-5 was our in-orbit demonstration and validation mission within Mission Possible with NICS. 26 and 7 will be development of a full-scale product, and then we have programs like Terra and Nova, where ESA aims to put 40 people on Moon by 2040. And this is our longer target. And I would like to invite Abhilash, because we have video, and this is how I would like to end the presentation. Thank you.